Good afternoon or good morning to everyone. So welcome and thank you for joining this session of MIDAS webinar. My name is Mark, and this webinar I will be sharing some of my experience in designing a reinforced concrete solid slab deck. So I will be talking about the reasons behind choosing solid slab deck and how does a solid slab behave and how do we analyze it. I will also share some of the things that I think we all should take note when we are performing the computer modeling. And I will also talk a bit about the wood and armor moment, support moment rounding, and also the optimization of the deck. And I will also talk a bit about the drawings, which I think is quite important. So at the end of the webinar, we will have a session of question and answer, about 10 minutes, so everyone can post their questions then. Okay, so this is the bridge. It is a U-turn above an existing road. It has 2 spans, 3 piers, surrounded by slopes. The space for it is quite tight. The turning radius is only about 24.4 meters. It is not a fan shape like this. It is quite irregular in its footprint. Here you can have a closer look at the bridge. So the perpendicular span of span 1 is slightly greater than 15 meters and slightly less than 15 meters for span 2. The centerline curve is about 16.3 for span 1, 17.6 for span 2. Not quite a big difference, but you can see from the plan view that both spans are actually quite different. So there are 3 piers and each and every of them is different. So this one is the longest pier. I call it abutment 2, 19 meters long, 10.25 column spacing. This is the smallest pier, which is 12 meters long, 6 meter column spacing. Quite an irregular configuration of the bridge. So the reasons behind choosing solid slab as the bridge deck, firstly is because of the short span. It is within the range of 15 meters. Secondly is because of the tight radius. Straight beams, say for example from this point to this point, if we put a straight beam here, at the middle the slab cantilever would be too much. It would be around 1.5 or 2 meters. That would be too much. And precast curve beams are actually not practically available. And if you do in situ curve beams, it is much more difficult. So for solid slab, we can also choose not to pre-stress it and only use conventional in situ reinforced concrete type of construction method. So that also means that we have a great ability to build the deck to suit whatever irregular shape we have, as shown here. And also, it would also mean that it is less expensive than other types of deck. So generally, solid slab deck for under this circumstances is more constructible. However, one shortcoming of the solid slab is it is much heavier in its self-weight comparing to other types of deck. But when we look at all these benefits that we will have, the savings in the cost, the time, the construction method can more than compensate for the heavier material cost. So what is a solid slab? How does it behave as a bridge deck, and how do we analyze it? So solid slab is basically a plate transferring reactions in all directions within its plane. So here is a typical cross-section showing how a solid slab is. So it is isotropic, meaning that it is continuous and uniform in mechanical properties in all directions within its plane. So they are also anisotropic slab. The second diagram here is a composite solid slab deck. So they are a series of beams arranged next to each other and infilled with in situ concrete. The longitudinal stiffness along the beam axis is much greater than transversely. So we call this orthotropic slab. The last two diagrams here show a type of two types of voided slab. Voided in comparing to solid slab, they are voided. When these voids are less than about 50% of the overall dimensions, the effects of the voids would be considered insignificant in affecting the deck behavior as a plate. So otherwise, it will be, the extreme case would be like multicellular deck, a box girder or multi-cell box girder, something like that. So how do we analyze them? Before we have our computers, grillage analysis is the most common way in analyzing all kinds of bridge decks, so including solid slab. So there is a grid system of longitudinal and transversal beams to distribute the load in both directions. So only when computers are widely and easily available nowadays that finite element method started to become more common. But grillage analysis is still, I believe, a much common method and used by many designers. So for finite element method, we are using a computer, of course, but how to simulate the bridge deck in the computer. So here is a diagram showing how I cut up the deck into elements. So I used square four-sided elements arranged in such a way that the square sides are matching the intended reinforcement directions, which are horizontally and vertically across the screen. So of course there are situations where square elements are just not possible. For example, along this curve edges here, you can see that I'm using triangular, irregular triangular shapes, and also above the piers, I'm using rectangular four-sided elements. But whatever shapes of elements that we choose, I suggest to avoid extreme aspect ratios, which means try avoiding very slim or very sharp pointed triangular and whatever shapes with extreme aspect ratios. So this exercise is took a long time. It's quite meticulous. So the larger the elements, the less accurate. But the smaller the elements, the more elements you will have and the longer time it takes to analyze. Here I'm using 500 by 500 mostly. So it is quite meticulous. As I said, I was a bit obsessed with getting all elements as ideal or as perfect as possible, but that was a mistake. So my experience is that don't get too obsessive about the shape and the configuration of the elements. Always stay practical when cutting up the deck into elements. So when we use computer in helping us to do our analysis and design, always keep in mind that nothing is perfect, nothing is flawless. Every software has its own limitation. So always check for errors, double check, triple check, keep mindful of errors always by both machine and human. So here I'm showing a screenshot of the computer model of this bridge. You can see that there are some elements popping up from the top face of the deck. It turned out that the positive direction of these elements in the local coordinate system is pointing in the opposite direction than other elements. So if this error was left unchecked, the reaction, the results, moments and shears of these elements will be having opposite sign conventions than the rest, and it would lead to an erroneous output as well. So checking is important. We have to also check on the boundary conditions, say the connection between the deck to the crosshead and the crosshead to the columns, and below ground the soil spring, the support for the piles, the support degrees of freedom, etc., which is especially important for this kind of integral bridge. So again, we have to check and always check. It is important, I think. So MIDAS is very helpful in this area. So it has a very user-friendly interface We can renumber nodes and elements easily. We can group them up, and we can also realign the local coordinate system easily. So we will cover some of these functions in day 2 of this webinar. So that's the geometrical modeling. So let's share a bit about the traffic loading to the bridge. So the contents here is more to those who are not familiar with BS5400 and BD3701, which are used to design this bridge. So notional lanes are set out for the application of traffic loads. So what are notional lanes? So this bridge in actual is actually a unidirectional and single lane U-turn. So there is only one actual lane. The reason for it being such wide is because for the road user to make their cornering safely. But it also means that we have to design for a sufficient rigorous structure for it to be intact. So notional lanes here, you can see they are actually 3 lanes. They are not the real traffic lanes, but they have to cover the full width of the carriageway. So including all shoulders and widths beyond the edge lines. So I just suggest that to draw it out and keep a record of it for future revisit. So the traffic loads from BD3701 have 2 types, HA and HB, and within these 2 types, there are many variables in each type. So for example, here is a figure showing a HB vehicle. So it says that the distance between the 2 middle axles should be 6, 11, 16, 21, or 26 meters, whichever gives the most severe effect. So if we are using computer software like MIDAS Civil, it helps covering all these variables much more easier. So other variables include a vehicle straddling between 2 lanes, and also like the loaded length of HA loading. So lastly, these 2 edges here, they are 2 walkways for pedestrians, so we have to also include the pedestrian loading. So that's the geometrical modeling and the traffic loading that I wish to share. So let's say we have analyzed the model and we have got our results. So what to do with it? Let's talk a bit about wood and armor moment. So the contents here are actually my personal understanding. It is just to help you and me to visualize the problem. It is not necessarily correct mathematically, but just to help you understand the problem. So let's say here is a plate within a larger plate. If we have a twisting moment here, this corner will rise and this will drop. So the elements is actually becoming longer, and this elongation will mean tensile stress, of course. So this stress is in addition to the stress created by the bending along the same axis. So the mathematical solution for this kind of twisting moment has been given in 1968. So it has to be accounted for. Sometimes the wood and armor moment would be insignificant, but sometimes it would be very significant. So another thing that I want to share is about the negative moment or hogging moment above the support of integral bridge. Is something like the hogging moment of a continuous beam. So in my experience, this negative moment is mostly more governing than the sagging moment at mid-spans. So let's look at how do we consider in making it lighter. So you can see here at the intersection of a horizontal component with a vertical support, there will be a peak moment, and this peak moment is calculated assuming a stick support with no width. But in actual case, every support comes with a width d. So the support reaction R should be distributed across this width, and this will counteract with whatever load above the horizontal component, and the peak moment should be therefore less than the theoretical peak hogging moment. So this is a diagram from this book by Mr. Robert Benin that I read. So for those who are interested, can go and have a look for the more detailed information. So another approach for reducing the support reaction is simply considering the horizontal component to stop short at the face of the support. So the moment at the horizontal component will be even lesser than the rounded negative moment. So even less conservative. So what kind of treatment to be used is actually up to the designer himself or herself. So, but I think this kind of reduction is very much useful in getting our design more optimum and efficient. So that's why I want to share this content here. So let's say we have all our bending moments, shears, our reactions. So we proceed to doing our reinforced concrete design. So for this solid slab bridge, I expected the bending moment to be governing over shear. So that is why I designed the slab first against the bending moments, then I checked against the shear resistance. So the flexural sectional design was carried out for both SLS and ULS as usual to BS5400. So to do this, I made two computer spreadsheets capable of iterative calculation. So they are made to make my input quicker and make my work easier. So there are commercial software available outside. So I was also told that MIDAS Civil is actually working hard on incorporating the section design of AS5 400 into their software. So let's look forward to it. So this is the this is how I did the RC design. So I took the section that has been designed for bending moment to check against punching shear. So punching shear comes from the vehicle wheel load. According to BD 3701, the effective pressure of both HA and HB should be 1.1 megapascal, but the total wheel load is slightly different. And you can see here the contact area based on the pressure and the load is also slightly different. So for square contact area, you can see that both is within the range of 300 millimeters square. So that is why I mentioned earlier that when we cut up the deck into elements, it is quite useful if we can cut it into 300 by 300 millimeters, so that we can apply a single wheel load easily onto one element. So the load dispersal through the slab depth is also allowed in BD 3701, but usually I do not apply the clause simply because that it is difficult to consider the depth of the neutral axis, because it would be different from each and every element and each and every load cases. So only when the capacity is marginally exceeded, then only I will come to this clause to check if I use this dispersal, it can pass. So the punching shear resistance is carried out conforming to BS5 400. So here is the requirements tabulated in figure 5 of the code. So they are very straightforward and can be easily done using a computer spreadsheet. So I'm not going to go into detail on this. So we have done our design. So there is room for improvement. So as I said before, for solid slab bridge, self-weight is always a big contributor to all the reactions of the bridge. So the first thing I looked when I aim for optimizing the bridge is to reduce the self-weight. So cutting down the self-weight would give a lot of reduction in terms of savings to materials, labors, times, and so on, which all would contribute to cost savings. So how much to cut down, how much to reduce? So my rather straightforward method is simply trial and error. So it is tedious, because it would mean that you have to do many designs on the same bridge, the geometrical modeling, the loading, everything. So so here you can see that this is the final configuration, the deck configuration of the bridge. You can see here at the midspan, the thickness has been reduced from 850 to 600. So here, there will be some tapering zones. So for these tapering zones, I'm still using flat elements. So each element here is of the thickness of the average thickness of its solid slab there. No tapered elements has been used. So this reduction is about 25% of the initial configuration, which is quite significant, I suppose. And this would also contribute a lot to the substructure, the crosshead, the columns, and the pile foundation as well. And so now let's talk a bit about drawings. I've always believed that drawings are engineers' words. They show how good or how bad a design is. So if I mean, aside from the completed bridge itself, drawings are the end product of a design. So if we give bad drawings to the contractor, bad things could happen. Here, this is a cut print of the reinforcement drawing of this bridge. So you can see that, as mentioned before, the main reinforcement directions are horizontally and vertically. So that is also the global spanning direction of both spans. But you can also see here, there is this area where the global spanning direction is more angled to the piers instead of perpendicular. So of course you can argue that all the twisting moments, the shears, and whatever reactions has been accounted for during the reinforced concrete design, but I still added in some reinforcement spanning this way, simply because what is the cost of a few more reinforcement in comparing with 120 years of structural integrity? So 120 years is, of course, the design lifespan specified by the code that I'm using. So here is the longitudinal section of the bridge with the scales different horizontally and vertically. So what I want to show actually is the reinforcement here at the end of the tapering area. A larger view is here. So the bottom reinforcement of the tapering is clashing with the horizontal reinforcement from midspan. So my boss actually noticed this before we issued our drawings. So we decided to bend up the ends of the reinforcement from the tapering zones so that they would have proper anchorage. So at the end of the day, if the drawings have not captured this, either if the contractor is good enough, they will come back to you asking for how to treat the reinforcement at this area, or they will, something else will happen. So that's why I think drawings are important. So here, lastly, is a typical cross-section, transverse section of the deck, showing the walkways on both sides, the parapets, and how the reinforcements are. So drawings are to regularize the irregularities. So as a designer, satisfy yourself that the drawings that you are going to issue are all good. Okay, so I remember in the invitation to this webinar, it has mentioned that I have designed 2 bridges using Solid Slab. So this is the other one. It was built a few years ago in Malaysia. It has 8 span of Solid Slab deck, and actually another 8 span of beam and slab deck further up the bridge. So the reason for the last 8 span to be Solid Slab deck is also because of the tight curve that we have there. So different from the previous bridge, this bridge has a single column pier here. So the original design was a rectangular deck without any tapering at the bottom. So as I said, there will always be a chance to make it lighter because Solid Slab decks are heavy. So of course many trials have been performed, and this is the final section, 400 thick at the edge and 650 at the center. So here is section 2.2, which is cut through the pier columns. You can see that 2 layers of reinforcement has been provided to resist the negative moment or hogging moment at this area. Yeah, and this is another example that I read from a book by Mr. Hamley. So you can see that it has a unique pier, a 4-point supported pier with a hinge base, and the abutment has a series of cord bearings. So the difference in the bridge supports between the abutment and the piers would mean that the deck will sustain twisting moments. So wood and armor movement could be insignificant, but most of the time they will be significant. So yeah, we should account for it. Yeah. So lastly, I would like to recommend to you all some further readings for if you all are interested. Thank you very much for your time. Stay strong, get well, wash your hands, and stay healthy. Thank you. Goodbye.